Hello and welcome to today's Flan Talk. We have Andy Young here with us today. Andy just started his PhD as at the Notre Dame University under David. And today he will present his paper on mask heart attention transformers in Boolean RASP, recognizing exactly to star free languages. And thank you for joining us today. And Andy, you can take it from here.
Okay, so yes, this is a paper about mass heart attention transformers and Boolean RASP, and we will discuss what both of these things precisely are in the rest of the talk. This is with Dana, David, who are in the chat. So if I say something horribly incorrect, hopefully they can correct me. But yes, and we're going to spend a couple of slides giving a brief overview of the background info, which hopefully is familiar to most people here, but we will go through just in case. There we go. So in the big picture, this is another piece in a long line of, or right now, a fairly long line of work looking at the expressivity of neural networks, specifically from the perspective of formal language theory. And the idea is that we consider transformer encoders as acceptors and rejectors of strings, and then we compare them with other known formalisms, for example, logics. And we want to say, like, what languages are recognized by transformer encoders and what languages are defined by logical formulas and how they intersect. For interested readers, they can look at the very recent survey, Transformers as Recognized as Formal Languages, written by Dana, David, and Will and Gail, I think. Yes, so please check that out. Again, some questions to keep in mind for today and tomorrow and beyond are, specifically what can we say about the expressivity of these models? And then what will that tell us about what they can learn in practice and how this may help us understand them and improve the models. Okay, so in a nutshell, these are the results from the paper. On the left-hand side of the diagram, we consider a couple models of transformers, and we relate them to these classes of these formalisms in formal language using Boolean RASP, or which will B-RASP as a intermediary step in the proofs. We'll return to this diagram a few times, so I'll keep going. And in the big scheme of other results, so I flattened the diagram on the previous page to the very bottom line here. We consider augmenting our model with positional embeddings, and that gives us more equivalences, and this falls into the line of other results, particularly a recent publication by Pablo Barcelo, Anthony, Vladimir, and Sasha. They also considered heart attention transformers and what logical languages they accept. But we find, as we see at the very bottom, one of the very few exact correspondences in this area. So between mass heart attention transformers, first order logic over strings with order, and B-RASP. And another thing of note is B-RASP also takes inspiration from RASP up here, but there is not, RASP compiles into transformers, but does not compile out of them, as opposed to B-RASP, which goes directly from mass heart transformers in and out. Okay. Any questions so far? If not, I will move on. Okay, so what is a masked heart attention transformer? Sometimes these terms can be overloaded, so we're gonna hopefully be precise about what model we're considering in our results. So here's the rough schematic of our model of a heart attention transformer. So we have our encoder has a heart attention module or a heart attention layer and also a position-wise layer. So in our heart attention, the idea is we model it as each position only attending to one other position. So, and we also use masking in our model. So the idea is we can add either strict future, strict past, or no masking in our model. And the keyword strict is actually important here. So in the standard definition of attention masking, each position attends
Muéstrame
positions.
que habían dado ese momento. No, pero el de
Okay, do you have a question?
Theta? Oh, I think that was an
Okay.
accident.
All right. Yes. Yeah. So in our definition, we only allow positions to tend to positions strictly less than itself with strict feature masking as opposed to the standard definition with less than or equals, which will become important later to note. Okay. Yes. We can go through this later, but the idea is we mask, we assign each unmasked position the score. We choose the position with the maximum score, breaking ties with leftmost or rightmost. And then we calculate a value and we add a linear function with a residual connection to calculate the value. And furthermore, we have the three-layer feed-forward network. This is different from the standard definition with 2 layers, but the 3 layers is convenient for the proofs and they can be simulated using 2 layers. Any questions? Okay, we also talk about B-RASP, Boolean RASP, and probably the best way to go through Boolean RASP is to give an example for intuitively how it works. So the example we're going to consider is writing a program in Boolean RASP. Specifically, we're going to write a program to recognize a Deek language, that is Deek 1 of depth 2. This is the example in the paper for anyone interested. So yes. If there are no questions about this language, we're going to go on with the example. So the B-RASP program is a sequence of Boolean vector definitions. So each line here is what we call a Boolean vector. The first 3 we call initial vectors, and the rest are a mix of attention and pointwise operations. These will be explained in more detail later on. But the idea is that each line, when you define a Boolean vector, you can call upon the definitions of previous Boolean vectors in previous lines. And these Boolean vectors act upon the input sequentially. In the example we go through, we're going to go through the program trace of the B-RASP program. So this table is empty now, but it will be populated with the values that each Boolean vector computes given the input L, L, R, L, R, R, and we append EOS to the string for our program. And in our setting, we define accepting or rejecting the string based upon the very last position of the last defined Boolean vector. All right, so we're going to start going through what each of these Boolean vectors roughly do. So the one of the key characteristics of B-RASP is this thing called an attention operation, which you've seen before in the previous slides. The attention operation is supposed to be like how a attention layer in a transformer works. So you would read this saying you find the rightmost j left of I that maximizes the score Sij and return the value V of j. So this corresponds to the masking we're using. This is the score function we're using. This is our choice and how we break ties. And this is the value at the end of what we've calculated. And similarly, we have the rightmost and we also have the leftmost choice. So we're going to go through the line by line, the program. The first 3 lines are initial vectors. These are default Boolean vectors for each program of Boolean RASP. They're defined over the alphabet that the program uses. So each of these vectors determines the the symbol at each position. So you observe that the Q sub EOS vector is 1 only at the EOS, and Q sub L is 1 only when the symbol at position is L. Okay, I'm going to continue on, but stop me if there are any questions whatsoever. So we have our first attention operation, P sub L. This intuitively is supposed to indicate whether the symbol immediately to the left of position I is L. So this table is empty, but we're gonna populate it position by position. So here is roughly, we're gonna step through. So we start from position I equals 1, and we apply the mask, the strict future masking, so we can only tend to positions strictly less than I. In this case, because I is the first position, the default behavior is to only look at the very last position. So we look at the very uncovered, and we assign a score to all these positions, so there's only one. And we choose the maximum, the position with the maximum score. Again, there's only one. So the position J we choose is very last column. And at position J, we get the value Q sub L of J. We take that and then we place that in P sub L row as the value we choose. And I'll go through the next step. Again, we in position 2, that is our position I. We look at positions strictly less than ourselves, and that is only this column, actually. We assign a score to all these uncovered positions. So, and we pick the maximum one, that is here. We get the value Q sub L, and we place that here. And then we proceed on, we do the masking, we send the scores, then we choose the value, and then we place that as our value. We mask, score, choose, and value. Mask, score, choose, get the value. Mask, score, choose, value, mask, score, choose, get the value, and that is how we evaluate an attention operation. Any questions?
Might be useful to say what the semantics of P sub L are.
Sorry, what does semantics mean here?
Just the fact that P sub L is true if the symbol immediately to your left is an L.
Mm-hmm. Yeah, P sub L is true if the symbol means left is L, yes, and we know that is here. I mean, if we go step back, what piece of roughly what P sub L do is you look at all the positions left of it, and then you pick the rightmost one, and that will give you the one directly to the left of it. And then the value function lets you decide whether that position is Q sub L or whether that position symbol in the position is L or not. So that's how this attention operation works. And similarly, we have S sub R, which indicates whether the symbol immediately to the right of the position is an R. And this works symmetrically to P sub L. So here we're using leftmost, we're using past masking, and we're using the same score function. And Q sub R is our value. So this looks at, of all positions to the right of I, we pick the leftmost one, and then we check whether that is, no, all positions, yeah, we check whether that is R or not. Okay.
Do you have other examples if it's not, the masking is not, it's not a 1, but something else instead there?
Yeah, so in a couple of slides we'll look at it. I didn't go through the entire program trace, but we'll have an example on the right soon. So after this, right now we have I, the vector I, which indicates whether the position I is in a consecutive pair L and R. And roughly what this is called a pointwise operation as opposed to an attention operation. So we don't have the attention operator symbols, but this says whether this checks whether we're at an L and we have an R to the right of us, or we're at an R and we have an L to the left of us. And here we have a V sub L, which is a this vector registers whether there's a violation of the deep one of depth 2 conditions. And here we have a score function that is not just one. So what this does is we look at a position I. If the position I is in L and it is not immediately matched, and the next not immediately matched symbol is not R, then we register a violation. And here we're using the score not I of J, that is the model checking the not next not immediately matched J. So we're looking at all the J's strictly greater than I, and we're picking the leftmost one such that it is not immediately matched. That is picking the next not immediately matched symbol. Okay, and then similarly, we can define the violation vector in the other direction, V sub R, which registers the violation if we have the symbol R is not immediately matched and the previously not immediately matched symbol is not L. And we say that if there are no violations of these kind anywhere in the string, then we should accept the string. So we define a final vector, y, which is our output vector. This basically, by using our mask here is 1 as well. So we look at everything and check that there are no violations anywhere. And here the value in the final column is true or 1. So then we accept in our model. Any questions? Okay, so hopefully that gives a taste of how B-RASP works. So B-RASP sits here at the middle of all our results. And so right now we're going to discuss how B-RASP relates to masked hard attention transformers. Originally, B-RASP was originated in thinking about Boolean transformers specifically, but the results also apply to masked hard attention transformers, and that's the one of the models we'll talk about in the presentation. So, and if you're interested, you can look at the paper for more information about Boolean transformers. Okay, so how do we get from Boolean RASP to transformers? We'll just touch on several aspects of the proofs in the rest of the slides without going too much into detail. So the idea is that B-RASP and transformers already have a very tight correspondence between how they work and were designed. So we can convert Boolean RASP programs to be simulated by a transformer just by the proof goes by rewriting the formulas in Boolean RASP, Boolean vectors in canonical DNF, and these when divided up in this way, the formulas are naturally simulated by layers in the transformer. I stumbled a bit, but hopefully the idea gets across. And similar in the other direction, which may seem strange if you think that there are a lot of values or the inputs to the masked hard attention transformers are real valued. So, but in actuality, because of the hard attention and how the encoder works in our model, the transformer only uses a finite set of activation values on any of its inputs. Therefore, this can be represented with log n bits and as formulas in B-RASP. So roughly the idea is that the attention layers in our model correspond to attention operations in B-RASP. The feed forward layer corresponds to the pointwise operations in B-RASP, and the word embedding corresponds to the initial vectors in B-RASP. Cool. Okay, so that's the idea of one side of the correspondence. We furthermore have a large set of correspondences on the right-hand side of a diagram as well. So B-RASP recognizes the same languages as all these formalisms. So we have counter-free automata, star-free languages, or we can say star-free regular expressions. Actually, so counter-free automata are a class of finite automata with a certain condition on the loops that I am not 100% certain how to say formally, but we can think of it as equivalent to the star-free regular expressions, which are those only using union, concatenation, and complementation. So this is the definition of the language of all strings that do not contain consecutive A's, which is definable as complementation and this stuff. This is also furthermore recognize the same languages as first order logic on strings with order. And here's an example which you can define using the language, this language. So we can define a successor function of two positions. And finally, we also have linear temporal logic, which is it's a logic used for talking about stuff that happens on a timeline. Like you can say that one of the operators in linear temporal logic is the until. So you can say that phi1 and phi2 hold until phi3 becomes falsified. So all events on a timeline. Okay, so we're gonna go through a little bit on how these proofs were done as well. We were able to, you can convert Boolean RASP programs to first order formulas. And this is pretty straightforward because Boolean RASP programs each Boolean vector is roughly a Boolean formula. So you can, with a careful translation, you can simply just translate into first order logic formulas. So this is fairly straightforward, but the other direction, trying to represent an arbitrary first order formula in Boolean RASP is very non-straightforward. One of the reasons is that in a first order formula, you can have as many quantifiers as you want, so you can introduce a bunch of variables. And that is not very naturally represented in Boolean RASP. As we noticed in our definitions earlier, we only use variables I and j, but in any first order formula, you can have many variables, so the formulas can become more complicated. This is noted by Kemp. His PhD thesis was Kemp's theorem, which proved that any first order formula can be converted into a formula in linear temporal logic. And it is over 100 pages, so you can get the idea that this conversion is not very trivial. There recently, or 2006, I think, Alexander Rabinovich put out a shorter proof of Kemp's theorem, which is 6 pages long, but it still has been not trivial to understand. Yeah, but the idea is linear temporal logic is talking about events on a one timeline, so they only just have one formula to talk about the position in time. Because of this, it is actually very natural to convert from linear temporal formulas to Boolean RASP programs. You can think of the same way that in attention operators, you only look at other positions on the same line. That's kind of corresponding to how linear temporal formulas talk about things on the same timeline. So with this trio of results, we can get the exact correspondence between the languages recognized by Boolean RASP and first order logic over strings with order. Cool. Any questions so far? Okay. So we note that this is not the only way to get to first order logic we can also go, this is not the only way to get to first order logic from Boolean RASP and back. We can also go to it via the counter-free, automata, and star-free languages. So there's these nice, very neat results that first found a correspondence between star-free regular expressions and first order formulas, and then from star-free to counter-free automata. These are fairly old results, at least compared to the other ones. And then we can actually get from counter-free automata to Boolean RASP. The idea is to use the Krohn-Rhodes decomposition of the automata, and counter-free automata can actually be composed into a cascade of identity reset automata, which have nice the transition and state properties mean that the transitions, the cascade can directly be simulated in B-RASP, or with a little work, but is very, 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 very neat correspondence between each identity reset automata and lines in B-RASP. Okay, so the idea is that there's very tight correspondence between Boolean RASP, mass-order attention transformers, and all these other formalisms, which is very interesting. So we got there. There are two ways to get. There are two loops to get. Two ways to get there that we've shown in the paper. Okay, if there are no questions, I'll move on again. So you might ask, if this correspondence is so natural, is that just because of how nicely we've defined B-RASP? And to touch on that question, we defined several variations of B-RASP in the paper that we've also shown are exactly equivalent to all these formalisms. But we've noted that one of these definitions is not equivalent, and that is using non-strict masking as opposed to strict masking. So in this setting, strict masking is actually important because we note that strict masking B-RASP programs are strictly more expressive than non-strict masking programs. And that's because the proof goes that no program can recognize this language that contains the single A. That's because our model only uses strict masking to represent positional information. So when we have it with non-strict masking, it is unable to distinguish between positions, and thus any program that accepts any program that accepts the string A must also accept the string AA and AAA and etc. So
Sorry,
it'd be interesting.
can you quickly say again what was strict versus non-strict masking?
Yes. I'm not sure of a perfect slide for this, so I'll just say it. So strict masking is non-strict masking is allowed to attend to positions less than or equal to itself. So position I can look at all j less than or equal to itself. Strict, we don't allow the equals.
Mhm.
Okay. And then you might ask, what happens if we add positional embeddings in to try to overcome this? And we looked at what happens to the model when you do add positional embeddings. So when you add sinusoidal position embeddings to the base model, so these are mass hard attention transformers with sinusoidal position embeddings, you show that these recognize exactly the regular languages in AC0. And this follows from first by finding correspondence between mass hard attention transformers with sinusoidal position embeddings and FO with the order and a modulo predicate. And then by prior result by Mix Barrington, we have that this logic recognizes exactly the regular languages in AC0. And we can move up a little bit. If we consider the class of math hard attention transformers with access to finite image positional embeddings, we find that these are recognize the same languages as FOMON. So that is first order logic formulas with access to all monadic predicates. This touches on a result. This touches on the work in the Barcelo paper, which looked at U hats and A hats, which are unique hard attention transformers. And they found FOMON as a lower bound for unique hard attention transformers. They asked if anything had an exact correspondence with FOMON, and we suggested this as an answer to that question. Any questions? Okay. Here we go. So those are a bunch of there's the taste of the proofs from the paper. And one might ask, so what? What next? Some questions that we might have been thinking about were, extending these results from hard attention to average hard attention is something to think about, going from these simpler models to slightly more complex models. And as always, what does this say about learnability? What do these results on formal expressivity actually have to say on what is learnable in practice? And furthermore, we had the note earlier about strict masking and non-strict masking. I don't think I put a slide for this, but there's actually some interesting observations we made about softmax attention. So soft attention transformers without positional embeddings. I think it was Misha 2020, they suggested that without a BOS token, soft attention transformers suffer a similar problem as mentioned before, where they cannot distinguish between positions. And so they argued that they cannot, the soft attention transformers without positional embeddings cannot recognize DEEC1 of depth 2. So there's some connections between hard attention and softmax attention and position recognition that might be interesting to observe in the future. Okay.
So what was your idea here about learnability? Like, what is your question here?
Oh, the question is
Here
just,
was like encoder and like expressivity as recognizer. So where are you going here with learnability?
I did not have a specific direction with learnability. It was just a question with whether this, I guess one direct question is what languages can hard attention transformers learn to recognize?
Okay.
But yeah, there was no specific question here. It's just what it would be interesting to look to see how these results say correspond to what is learnable by hard attention transformers.
Mm-hmm.
Any other thoughts or questions? Okay, if not, that is the most of the content I was going to go through. So thank you to my lab mates and Lena for helping me with this. And then we'll have a conclusion, any questions slide. So we went through mass hard attention transformers. This is sort of like a base case for other results in this area. We looked at B-RASP and its equivalences. We give a brief overview of how the proofs work. We touched on strict masking and non-strict masking, and we also considered position embeddings. Cool. So open to any questions, comments, or concerns.